Alright, so the previous lesson we did an introduction to confidence intervals, and today we're going to look more specifically at constructing a confidence interval of a population proportion. So remember, this is when our study is, a question like one of these right here. What proportion of U.S. adults are employed right now? So we get an estimate from our sample, right? Maybe we surveyed 100 people, and out of those 100 people, 10 say that they're unemployed. So our estimate would be 10 out of 100 is 10%. So our estimate would be that 10% are unemployed, right? But what you want to look at is what's an interval around that 10% estimate that we can be confident in, okay? Same idea of what proportion of high school students have cheated on a test. That's probably like 95%, honestly, right? So that might be our estimate that we get when we do a sample, and have an interval around that. Now, the real number might be 90%, but, kids are probably going to lie. And remember, we call that response bias, right? Remember that term we learned a long time ago? Whenever you ask a question that someone might not want to answer truthfully to, so it makes your data be off from what the real number is, because people lie sometimes. Of course, these other examples right here, what proportion of pine trees are infested with beetles? So these are all examples of proportions that you might be interested in, that you might need to know an estimate and a confidence interval of. All right, so those are just some kind of things to get us in the right frame of mind. So before you do these, you got to check conditions to make sure these conditions apply. So first, it has to be random. We talked about this yesterday, right? It's got to be a random experiment, or some type of random data that you're getting. It has to be independent, which means individual observations can't affect other observations. And then the 10% condition must be met, which means that most of the time we sample without replacement. So this condition has to be checked to find a standard deviation. And remember, that condition is that you can't sample more than 10% of the population. So if you have a population of 1 million, then your sample has to be less than or equal to 100,000, right? 10% of 1 million. So you can't sample more than 10% of your population. All right, and then the large counts. So this is where we check the condition to make sure we can treat it as normal. Remember, it's approximately normal if n times p hat and n times q hat are both more than or equal to 10, right? We check that condition, and if that's true, then we can treat it as normal. All right, so let's go on and look at constructing a confidence interval for p, the formula. So we looked at this formula briefly in the lesson before. Our statistic is our estimate, our p hat, right? It's the estimate of our proportion for our population. So this is really our sample proportion right here when you have p hat. P is the actual population proportion that we're trying to estimate. And then you're going to add or subtract a critical value that we'll figure out how to calculate in a second, times the standard deviation of the statistic. All right, and the formula for standard deviation of a proportion we already know, and so I'll write that in here for us just to kind of remind us. So that formula for the standard deviation of a population proportion is the square root of p times 1 minus p all over n, or square root of p times q all over n. All right, so the issue here is that we don't know what p is. We don't know the actual population proportion. That's what we're trying to estimate, right? P hat is trying to estimate what p is. So we don't really know what it is. You're like, well, I remember we knew what it was before. Yeah, that was when we did an entire sampling distribution, right? So that's when we would find all of the different possible samples, remember, and we would get the dots, and most of them would be in the middle, and then there would be a few here and a few here, and we would get that whole distribution, and we said that the average of all of these samples is p, right? The issue now is that we're not taking a lot of different samples. We don't want to have to take a lot of different samples to find p. We're just taking one sample, right? We're going to survey one group of people. We're not going to do a bunch of different samples. Like, remember when we did the marble drawing? We had 200 marbles, 100 were red, 100 were blue, and we used our calculator to randomly get numbers that were represented either red or represented blue, and every student did it like 10 or 15 times to get all these different samples. Well, we're not doing that this time. We're just doing one sample out of our population. So since we're just doing one sample, we don't have the population proportion. All we know is the sample proportion that we got as our estimate, right? So we're going to replace, in this formula, we're going to replace P with P hat, okay? So this really, for this example, is going to be called P hat, all right, and not P. So because it's P hat, this isn't really the standard deviation, okay, because the standard deviation is when it's P. But since we're replacing with P hat, it's not the standard deviation, we call it now the standard error. Okay, so that's the term we use for that same formula, but using P hat instead of P. Okay, so this is what we're going to find. The standard error is what's going to really go in here, not really the standard deviation. It's really going to be the standard error. All right, but it's essentially the same formula. You just have to use P hat instead of P. Okay, and how do we find the critical value? We use the Z table. All right, and we'll work on how to do that here in a second too. All right, so these are the three parts of our formula to find a confidence interval. So it's important that we know how to find each one of those. All right, let's go ahead and look at how to find a critical value. Okay, so finding a critical value. So for 95% confidence, so the critical value always depends on how confident you want to be in your data. Okay, so 95 is the most common one. So if we say we want to have a 95% confidence interval, so let's think about visually what that means. So if we've got our normal distribution, right? Oop, that's pretty bad. Again, I'm writing on this tablet, which is kind of hard to draw on. Let's try to make it as nice as we can. There we go. So in a 95% confidence interval, right, that means that our data is between here and here, right? That means we want to be 95% sure, so our data is somewhere between some value and some value, right? Okay, so thinking about the Z table, remember these numbers in the Z table, they tell us the percent that is from some value in the Z table and less, right? So the value of the Z table for a 95% confidence interval is going to be whatever proportion, whatever percent is right here, okay? So if 95% is right here, that leaves 5% left over to be divided up between this piece and this piece, right? So that means the percent that's below this z-score, right, is 2.5%. Okay, so what we're going to do is we're going to look up 2.5%, which is 0.025. We're going to look that up in here, all right, as close as we can get to it, and convert that into a z-score. And whatever that z-score is, that is our critical value that we're going to use in our formula. Okay, so let's look at 0.025 in the z-table. All right, 0.5, so we need to go way down here further somewhere. Let's see if we can find the closest one to 0.025. 0.0268, 0.02500, right there. Bam. Okay, so what is the z-score for this value right here? Let me underline it, and let's look and figure out what's the z-score for that. So that z-score is going to be negative 1.96. Okay, so our critical value then for a 95% confidence interval is going to be negative 1.96. That is what we would use in this formula for our critical value to find a confidence interval that we are 95% confident in. Okay, now let's do another one for 80%. Okay, so imagine visually again, let's do a little curve. All right, and let's say we've got an interval now that's 80% between these two values. That means that we've got 20% left over. So 10 of it goes here and 10 of it goes here. So this percentage that we're looking for in the table is 10% that's going to be below that z-score. All right, so we're going to look up 10%, which is 0.1000, however many zeros you want, and we're going to try to find which value in here is closest to 0.1000. All right, so right here is 0.25. Let's see, 0.1017, 0.00990. So it looks like this one is only about 10 thousandths off, whereas this one's about 17 too big. So this one looks like it's the closest one to 0.01, right? So that would be a z-score of negative 2.3, 2.33, right? So for this one, our critical value equals negative 2.33. I just realized I told you wrong. That's 0.00. No, that's right, 0.01. Yeah, I told you wrong. That's 0.01. We're not needing 0.01. We need 0.1. So I told you wrong here. Let's go back and find now the critical value for 0.1. Okay, so we're looking for 0.1 now. 0.09, 0.09853. 0.01027. So it looks like this one's about 27 tenths above, 10 thousandths above. This one's about 47 or 147 below, really. So this is the closest one that I'm seeing right here. So that would be a z-score of negative 1.28. That makes more sense for sure. So negative 1.28 would be the z-score we would use as our critical value to calculate an 80% confidence interval. All right, so you guys go ahead and try this one. Okay, so you try. This isn't on your paper, so you try. I don't know why that says Trey. You try to find a. Let's do a 99% confidence interval. Okay, so go ahead and pause the video, give that a try, see if you can figure out what a 99% confidence interval is, and then when you hit play, I'll go over the answer. Alright, so 99% confidence interval leaves 1% left over to be split up between the two tails. So one tail over here is going to be only 0.5% of the total curve. When you convert that to a decimal, that's 0.005. Then when you go to the table, we're looking for the closest to 0.005 right here. These two are the closest. This one's only 6 10,000ths away. That one's 8 10,000ths away. So that one's a little bit closer. So we'll go with a z-score of negative 2.58. Alright, so that would be the critical value that we would use to calculate a 99% confidence interval. And that's all the time, every time. If it's a 99% confidence interval, negative 2.58 is going to be your critical value. If it's 95%, it's going to be negative 1.96. So like I said before, 95% is the one that's most commonly used. So this is the one we're going to use the majority of the time as our critical value. But it's important that if on your challenge exam you see them ask for a different confidence level, you know how to calculate your critical value. All right, so let's move on and look at an actual problem here. So alcohol abuse has been described by college presidents as the #1 problem on campus. How common is it? A survey of 10,904 randomly selected U.S. college students collected information on drinking behavior. The researchers defined frequency binge drinking as having 5 or more drinks in a row 3 or more times in the past 2 weeks. According to this definition, 2,486 students were classified as frequent binge drinkers. Okay, so first, let's identify the population and the parameter of interest. So our population are U.S. college students, right? So the idea is to figure out how common is it for U.S. college students to be drinking. So our population is U.S. college students, not college students, right? Because that would include college students from other countries, not college age people, college students, people that are actually students in college, all right? And then the parameter, all right, our parameter, or P, okay, P for our population proportion, is the proportion of frequency binge drinkers. Okay, so that's what we're looking at. We're trying to figure out and estimate the proportion of frequency binge drinkers. All right, check conditions for constructing a confidence interval. So if we go back and look at the conditions that we said we've got to meet, first, random. The data should come from a well-designed random sample. All right, so let's see first, does it do that? It says it was randomly selected, so yep, it is random. Next, is it independent? All right, should be. we wouldn't really think that one student that we get that says they drink would affect whether another student drinks or not. Now, maybe, you survey two people at once and one says they do, so the other wants to look cool in front of their friends, so they say they do too. So I guess technically they could affect each other, but we're assuming that each answer is going to be independent of the other. We're not going to, we can't factor in response bias and, as far as independence. So look at a 10% condition. Are we surveying less than 10% of the population? So it says we surveyed 10,904, right? So if you multiply that by 10, right, that's our sample. If you multiply that by 10, which makes 109,040, we need a population to be more than that. So remember, let's think of our population, U.S. college students. Are there more U.S. college students than this? Yes, of course, there's way more college students than 109,000. There's like 30,000 by itself that just go to UT in Knoxville. So our sample size is definitely less than 10% of the whole population of U.S. college students. So meets that condition. The next one is large counts. So do P hat and Q hat both give you more than or equal to 10? So right here, we're going to check by doing our proportion. So let's take 2486 times 10 or over 10,904. Okay, and then we're going to go ahead and divide that. Right, so I'll pull up a little calculator here. 2486 divided by 10,904, and we get a proportion of 0.2279. So we could say 22.8% roughly. Okay, so the question is that times N, right, the number in our sample, 10,904, is that going to be equal to more than or equal to 10? So multiply that by 10,904, and you see what's going to happen right here, hopefully. It just gives us 2486, the number we had originally, right? I mean, when we calculate P, we divide by 10,904. Then when we multiply it by N, that gives us the same number we started off with. It gives us our sample value. So obviously, yes, 2486 is more than 10. All right, and if you subtract these, that'll give you Q. And then, of course, you go through the same process with Q. Q times 2298, whatever, is still just going to get, or times 10,904, is still just going to give you the value for Q again. So obviously, if you subtract 2,486 from 10,904, you're going to get a value that's bigger. It's going to be what, like 7,000? I don't even know, 7,100 and something. I don't even know what it is. We'll just make something. Obviously, it's going to be more than 10. So in this situation, yes, NP is greater than 10 and NQ is greater than 10. So it meets all of our conditions. So now let's actually do the meet, which is finding a 99% confidence interval. And it says show all calculations. So now we got to think back to the formula. So first is our estimate. All right, we're going to take P hat, which is our estimate that we just calculated, 0.2279. Okay, so I'm going to say 0.2279 plus or minus, and then we're going to put in the critical value, right? So our critical value, we just looked at how to calculate that using these. That means that we want to do a 99% confidence interval, right? Well, we just found that on the last slide. 99% confidence interval has a critical value of negative 2.58. So for our critical value, we're going to do plus or minus 2.58. Now, why did I not do negative 2.58? Because I'm adding and subtracting it. So if I add a minus, right, it doesn't, I'm still going to end up getting the same thing. I'm still going to be doing plus and minus it, even if it's negative. If it's negative, it'll be minus and plus, right? So it really doesn't matter the sign you put in there for the critical value. What matters is the number. Times, and then we're going to use the formula right here for standard error, which is the square root of P hat times 1 minus P hat over N. So that's what we're going to plug in right here. So we're going to do times the square root of p hat, 0.2279, times 1 minus p hat, which is 0.2279, and we divide that by n, which was 10,904. All right. Okay, so let's see if we can calculate that using this little tiny calculator. So let's do 1 minus 0.2297 first, or 0.2279. Okay, so this is the value in the parentheses. We're going to multiply that by 0.2279. And then divide that by 10,904. Okay, so we get this value, and we're going to take the square root of that. All right, now this calculator here doesn't have a square root, so I'm going to do it on my big calculator. You take the square root of that, you get 0.0040. All right, so rewriting this, I'm going to have a point estimate. My p hat is 0.2279 plus or minus, and remember these two together make the margin of error. We've got our critical value times, and this all gave us 0.0040. So now we multiply that times 2.58, and that gives us a margin of error of 0.01, right? Which, remember, these are decimals. If we convert to a percent, that would be about 1%, right? 0.0104 if I go out to the fourth decimal place. All right, so now we've got our estimate, plus or minus, and this is our margin of error. This is how much we would be off with a 99% confidence interval. So our actual interval are the two numbers that we think we're between. So we're going to add this to 0.2279. And when you add it, you get 0.2383. And then we subtract it from 0.2279, and you get 0.2175. Okay, so this is our confidence interval. All right, now the last thing we're going to do is interpret the confidence interval. So this is thinking back to what we did yesterday, right, when we interpret confidence intervals. So remember there was that phrase that we wrote down, right? So for this confidence interval, we would say that we are 99% confident that the interval, we are 99% confident. If you need to look back at the notes from yesterday, you can do that. That the interval from, and we can make it percentages if you want to, so we could say from 21.75% to 23.83% captures the percent of U.S. college students who, and remember what our population is, U.S. college students, and we're looking at the ones that are frequency binge drinkers, right? So these are ones percent of U.S. college students who are frequency binge drinkers, which is our population proportion. Okay, so that's the phrase that you want to try to use to interpret your interval. We're 99% confident that this interval captures the actual percent of U.S. college students who are frequency binge drinkers. All right, pretty confident in it, right? That it's somewhere between these two. There's still a 1% chance that it's really something less than 21.75 or something higher than 23.83%, but we're 99% confident somewhere in there. All right, let's go on and do another one. So what you do out there, you just completed the four-step process. We stated our parameter and what we wanted to estimate. Then we identified the appropriate inference method, right, and checked our conditions. We identified, we've got to use, the formula for the confidence interval, right, and find the critical value and all that. And we checked our conditions to make sure that those work. And then if the conditions are met, we actually did our calculations. And then the last thing is we have to find some conclusion. You've got to always take your calculations, right, and be able to tie them back into the context of the problem and actually come to some verbal conclusion that you can draw, right? If you can't explain what your data means, then what's the point of even doing the calculations, right? So you got to be able to explain what it means at the end. All right, so let's look at another one. All right, or maybe you guys can try this one. You guys go ahead and try this one. Then I'll go over it, and you can check and see how you did. All right, so try to do this one again. Just follow that same 4-step process. All right, so first we got to define the population. Our population are U.S. teens from age 13 to 17, and our parameter, which is our population proportion, which is the proportion of these teens who think you should wait until marriage to have sex. All right, number two, the thing we've got to do in the 4-step process is to check our conditions. So first, is it random? All right, it says a random sample, so check it's random. Is it independent? So we're assuming that these teens are, again, answering independently of each other. One teen's answer does not affect another teen's answer, so we can check that one off. The 10% condition, our sample was 439, times that by 10, so 4,390. Our population needs to be at least that, right? And our population is, again, U.S. teens from age 13 to 17. There are definitely more than 4,390 teens in the U.S. that are in that age range. All right, so then the large counts, we need to check to make sure NP is greater than 10 and NQ is greater than 10. Well, remember in the last problem, whenever we found N, to find N, we multiplied or we divided the number in our sample that said, whatever, by the total of our sample, N. That gave us our p-value, our p-hat. When we multiply that by N, it just gives us the number that said, the answer a certain way, right? So that value is what we're going to get when we do N times P. And then when we subtract that value from the total, that'll give us the value that we'll get for N times Q, right? Which we said was, 7,000 something or whatever. So right here, same idea. This number of people that said yes is 246. That's what we're going to get when we do N times P. That's greater than 10. And then whenever we subtract 246 from the total, that gives us what N times Q would be, which is 193, which is also more than or equal to 10. So all of our conditions are met. Now we can do the calculations, which is the third step. All right, so to do the third step, we think of our formula. And remember, our formula is first the statistic p-hat. Okay, I'll put it in black here. So we're going to have p-hat plus or minus the critical value, right, whatever that is. Okay, now one thing you'll see a lot of times used for this critical value is Z with a star on it. So this is the kind of the notation you'll see for critical value. It's Z, and up here where an exponent would be, there's a little star. So that is the symbol that you'll see for critical value. So just be aware when you see that what it means. All right, and you multiply that Z star by the formula for standard error, which is p-hat times 1 minus p-hat divided by N, and you take the square root of that. So that's what we're going to find. So first, what is our sample proportion? Well, our sample proportion is 246, right, that said yes, divided by the total number, 439. So 246 over 439. You divide that, and when you divide it, you should get 0.5604. So that's our p-hat that we're going to use for this formula. So we've got now to plug that in. So 0.5604 plus minus our Z star. So what's our Z star? Our critical value for 95% confidence interval. Well, save yourself time because we already figured that one out back here. 95% confidence interval, the critical value is 1.96. All right, remember, it doesn't have to be negative because we're going to add and subtract it. So we add or subtract 1.96 for our critical value, and then we're going to multiply it by this whole formula. P-hat, 0.5604, times 1 minus 0.5604, and then we divide that by n, which is the total number in our sample, which was 439. Alright, so let's go ahead and pause it, do that calculation. Divide that, and then put in the square root, we get 0.0237. So we've got 0.5604 plus or minus 1.96 times 0.0237. So 0.0237 is our standard error. Now we multiply that by 1.96. Again, remember, try to not round any of your numbers until you get to the very end. So even though I've rounded it to this, if you've got all this written out as a really long decimal, go ahead and multiply that by 1.96. Avoid the rounding until the very end if possible. Alright, so once we multiply that, we get 0.5604 plus or minus. Alright, and the numbers that I got before, whenever I did this without doing any kind of rounding, the numbers I got were 0.0464. Okay, now again, if you type that, you're probably going to get something that's a little bit different because the numbers might have been rounded off. But it should be about that, 0.0464. So now when you add that and subtract it, you get a interval, confidence interval, 0.5140 when you subtract it. When you add it, you get 0.6068. Okay, so this is our confidence interval that we can be 95% confident in. So then the last thing is to interpret. So now we can use our little phrase. So we can say we are 95% confident that the interval from 0.5140 to 0.6068 captures the actual proportion of U.S. teens aged 13 to 17 who think you should wait until marriage to have sex. Alright, so that's confidence intervals. Now, the other type of problem you might have on these is having to choose a sample size. So sometimes, maybe we know how confident we want to be, right? And we got to figure out, okay, before I even do my study, how many people should I survey, right? I want to figure out what should n be? How many people should I have in my sample so that my margin of error is a certain amount? Maybe before I even do it, I know I need my margin of error to be a certain percent off, right? So I want to figure out, well, how many people do I need to sample to begin with? Okay, so in these types of problems, all right, we don't know what p hat is yet because we haven't done our sample, right? We're trying to figure out how big of our sample needs to be. How many people do we need to sample? So there's no way to know what p hat is yet. So what we do is we use the value that will be on the safe side, right? So if p hat is 0.5, then that makes us have the biggest margin of error possible. Okay, so to be safe, to make sure we're not saying we have a smaller margin of error than we do, we're always going to make p hat 0.5 in these types of problems whenever we're trying to determine what should n be. All right, so if we don't know p hat, we're just going to make it 0.5 to make sure that we're on the safe side and our margin of error is as big as possible. All right, so let's look at one of these problems. So a company has received complaints about its customer service. Before hiring a consultant, the president wants some idea of the sample size that she will be required to pay for. The president wants to estimate the proportion of customers who are satisfied at the top two levels, and she wants the estimate to be within 3% at a 95% confidence level. Okay, so the big idea is right here, 95% confidence level. So that tells us that our Z star has to equal 1.96, right? That's the value for 95% confidence level that is our critical value. All right, now the margin of error, we want to be within 3%. So the margin of error is going to be 3%. So if we look at this formula, we know right here we're going to plug in 0.03. For Z star, we're going to plug in 1.96. And then like we said for p hat, we're going to do 0.5. And then 1 minus 0.5, well, that's just 0.5 again. And then we're going to solve it for n. All right, so that's the formula that we're going to have. So let me just go and copy that, and I'll paste it back over here where our problem is. All right, so now we just have to solve this. So first, we're going to divide by 1.96 on both sides. All right, so that'll cancel right here. And then when we divide 0.03 by 1.96, we get 0.0153, bunch of other stuff, right? So I'm going to put a dot, dot, dot right there just so we remember it keeps going. Again, try not to round until you have to. 0.5 times 0.5 is going to be 0.25 over n. All right, now we got to get rid of the square root. So to do that, we're going to square it. Square this. So we've got 0.25 over n equals, and we square that number. Again, hopefully you didn't round it from before. So that gives us 0.00023 42 blah blah blah, a bunch of stuff, right? And we've got 0.25 divided by n. Our sample size should give us this. So all you got to do right here is swap these, right? If 0.25 divided by n is this, then 0.25 divided by this is going to give us n. Just like if 6 divided by 2 is 3, 6 divided by 3 is 2. So all you got to do is swap those. And so n is going to equal 0.25 divided by this long decimal, 0.000234, whatever it is. So just on your calculator, you can do 0.25 divided by, and then put in, hit second answer. And when you hit second answer, it gives you a value of 1067.11111. Now, that is how many people you need to survey. So to be on the safe side, no matter what the decimal is, if it's more than 0, right, if the decimal isn't just 0 exactly, we've always got to go one person above that. So we're going to say 1068 is how big our sample needs to be in order to make sure our margin of error is 3% at a 95% confidence level. All right, so that's the number of people we should do in our sample. Okay, which is kind of cool to be able to figure out before you even do your sample how many people you got to sample in order to have a certain margin of error. All right, so let's look at another one. In the company's prior year survey, 80% of customers said they were satisfied or very satisfied. Using this value as a guess for p hat, find the sample size needed for a margin of error of 3% and a confidence level of 95%. So what they're saying right here is now we are using 80% as our p hat because we have data from the previous year. Right? So instead of using 50% as our guess, we're going to use 80%. But we're still going to use everything in the formula the same, except now P is 0.8, which makes Q over here 0.2. So everything else is going to be exactly the same. So we got 0.03. All right, and that's going to equal our critical value, which is 95%. So that critical value makes 1.96 again, times the square root. But now we're going to do 0.8 for P, times 0.2 for Q, because it's 1 minus P, divided by N. So once we divide 0.03 by 1.96, we get the same thing we got before, which is 0.0153. All right, and then over here we've got the square root of 0.8 times 0.2 is 0.16 this time. Okay, all the other steps are the same except that number at the end is going to be different. We square that and we get 0.000234. And over here we've got 0.16 over n. So the difference is now we divide 0.16 by that decimal instead of dividing 0.25 by that decimal. All right, we swap those around and divide it, and so we get n equals 682.95, so we got to round it to 683. So we need to survey at least 683 people this time. All right, so notice how whenever we used 0.8, the number of people we sample only has to be 683, whereas when P was 0.5, we had to survey more people. So that's why 0.5 is the one that helps us be on the safe side, because we end up surveying more people to make sure our margin of error is where it needs to be. All right, what if the company demands a 99% confidence interval instead? How would this affect the above answer? All right, when we say above answer, we're going to talk about the original answer, so we're going to assume 0.5 and 0.5 still. But now, if it says 99% confident, that's going to make the critical value change, right? So a 99% confidence interval, remember that decimal that we had before for 99% confidence? It was negative, it was 2.58, right? So we've got to use 2.58 for our CV this time, our Z star. So we would have 0.03, still the same margin of error, but we're going to have 2.58 this time for our Z star. Then we have square root of 0.5 times 0.5 divided by n. So this time we're doing 0.03 divided by 2.58 instead of 1.96. When we divide by 2.58, we get 0.0116. All right, and then we multiply our 0.5s. Same step as before. We square it. So we're going to square that value of 0.0116. That gives us 0.000135 equals 0.25 over n. Now we divide 0.25 by this long decimal, and that gives us n, which is 1,849. And mine has it exactly 1,849, which is interesting. So it's exactly 1,849. So you don't need to round it up too much. So how did that affect the above answer? Well, making the critical value bigger made our sample size have to be bigger, right? Because we want to be more confident. So if we want to be more confident in our estimate, we've got to have more people in our survey. That makes sense, right? All right, so now not only do I want to be 95% confident, but I want to be accurate within 2% points. How big a sample size do I need to take? So this time we're adjusting 0.03 to be 0.02. All right, we want to be 95% confident, so we're going back to 1.96. And we're going to have the square root of 0.5 times 0.5 divided by n. All right, so this time we're dividing 0.02 by 1.96, which is 0.0102. Multiply our 0.5s and then square both sides. So we square that number. Notice the steps are always the same, it's just different numbers you're putting in. So 0.0001 is what I got right there. And then we're going to divide 0.25 by that. 0.25 divided by, and I'm going to hit second answer on my calculator. And that gives me exactly 2,401 people. So that's how many I would have to survey to have a 2% margin of error, which again makes sense. The smaller the margin of error means you need to survey more people, right? If you want to be off by less, you got to survey more people. All right, you guys try this one. We'll go over it, and then you can go ahead and do these practice problems right here. Of course, anytime in these videos, if you feel like you understand what's going on well enough, you can go ahead and do your practice. Make sure you know what's going on. All right, so pause it. Then we'll go. All right, so when you set up your formula, of course, 0.1 is your margin of error. All right, and then 1.96 is your critical value because they set a 95% confidence level. And then P hat, we'll use 0.5 and 0.5. So we divide both sides by 1.96. That gives us 0.0510. Then to get rid of the square root, we square both sides. That gives us 0.0026. And then the 0.5s multiplied to be 0.25. So you just got to divide 0.25 by 0.0026. Again, try not to round until you get done this last step. And we get n equals 96.04. So because it's just a little bit over 96, we have to be on the safe side and say we need to survey 97 people at least to have a margin of error of 10% with a 95% confidence level. Okay, so go ahead and try these problems. Let me know if you have any questions. Send me a message on Remind or whatever you want to do, but just let me know if you have an issue. Thanks.